Hi, everybody. Now we're going to do 3.3, this video. So this is derivatives of products and quotients. In other words, we talked about the derivative of a function, what about the derivative of the product of two functions? Can't we, if we take the product of two functions and we want the derivative, is that just going to be the product of the derivatives? That's really the question here. So we have a little table here, explore and discuss. So capital F is a function x squared. Capital S is a function x to the third. And small f here is the product of f of capital F times small s, capital F times capital S, which of course is x squared times x to the third, which is x to the fifth. And we want to know, what is the derivative of this overall function? Is it just the product of the two functions, of the two derivatives, like choice A? Is it just one function times the other derivative? It's one derivative, what is it? So I have this worked out over here. So here we go. So here's the question. And now f prime, capital F prime is 2x, and capital S prime is 3x squared. That's the individual derivatives. And choice A is the product of those two individual derivatives, but I get 6x to the third. And we know that that's not really the answer, because the answer better be, based on this guy here, x to the fifth power, the answer better be 5x to the fourth. But anyway, let's look at the rest. F times S prime is 3x to the fourth. F prime times S is 2x to the fourth. And look at this crazy thing over here, choice D. F times S prime plus F prime times S. Now that is insane. And you get 3x to the fourth plus 2x to the fourth, which is 5x to the fourth. And like many insane things, it is actually absolutely correct, and is brilliant. And this actually can be proven to be true. I mean, this here we see, but I'm saying in general, we could prove this, and we prove it and that would be, whoops, wrong thing here. That leads us to a formula, which is called the product rule. So the official answer in words, the derivative of the product of two functions is the first times the derivative of the second plus the second times the derivative of the first. That was choice D. And we write it here as product rule. So it's F times S prime plus S times F prime. And of course you could write it this way. This is when you use primes, and this is when you use dx dy's. And like I said, they both mean the same thing. So just be aware of that. Okay, so here we have a product, 2x squared times 3x to the fourth minus 2. Now we could do this without the product rule. We could just multiply everything out and and then do it that way. In fact, we will. We're all going to do that just for just to show you that you get the same answer. But let's do it with the product rule. So the derivative of, so first we have this function here. The derivative of the second function of the parentheses guy is 12x to the third, which is what we have right here. The derivative of the outer guy is 4x, which we have over here, and we multiply that times the original. So this is following the product rule. And if we multiply those out, we get 24x to the fifth plus another 12x to the fifth minus 8x, which is 36x to the fifth minus 8x. That's what we actually get. Now we're going to do this by just distributing and multiplying out and just doing it the old-fashioned way, not even using the product rule, old-fashioned. It's funny because, just a couple of weeks ago, you guys didn't know any of this stuff. And now it's like, oh yeah, sure, old-fashioned, yeah, the old-fashioned way to do a derivative. It's literally every time you learn something new, it's like you're a whole new world, and it's as if that world is with you forever until you get to the newer thing, and then it's a new world. Anyway, here we're gonna just distribute it out, and when we distribute it out, we get 6x to the sixth minus 4x squared. When we take the individual derivatives, this sucker here is 36x to the fifth, and the derivative of this guy here, just with the basic power rule, is 8x, which is the same answer we got before. So you see, why is it so important? Why do I feel so important to do this twice? I want you to see that this stuff actually works, because we're throwing those like fancy wild formulas at you. But they really work. They really work. And by showing that different methods get you the same answer shows, to me, it shows kind of the validity or the consistency of all this. Now, here we want to find a tangent line. Now, now again, I could just multiply these guys out, like FOIL it out if I wanted to, but I don't. I'm going to use the product rule. So I want to, so what do we want here? We want to find the equation of the tangent line to the graph at x equals 3. That's question A. Question B is find the values of x where the tangent line is horizontal. And we'll get to B. Let's do A first. So in order to do A, first we just got to take the derivative like we did it in the previous example. Then, well, let's just do one step at a time. So f prime, the derivative of this overall function, it's going to be 2x minus 9 times x squared plus 6 prime plus x squared plus 6 times 2x minus 9 prime. And that's going to give me 2x minus 9 times 2x, x squared plus 6 times 2, because those are the different derivatives. And when I put this all, well, we're going to put it all together. Now, what we want to do, now, notice here that what they're doing in the book here is they're not even bothering simplifying anything. I personally would simplify this a certain amount, but they didn't even bother. So here's the thing, should you simplify? Should you not simplify? You have to simplify. If I give you a test, you need to simplify. So here's the story. And this is what my daughter's AP calculus teacher told them. I have a daughter who took AP calculus. I have more than one daughter who took AP calculus, but this is what they were told. If you, on the AP test, if you make if you write an answer and you don't simplify it, but your answer is correct, you can still get full credit. If you have a correct answer and then when you simplify it, you make a mistake simplifying it, and that leads you to now have an incorrect answer, you will lose points for that. So what I'm saying is, you don't have to. I personally like simplifying stuff, but you don't have to, and you'll still get full credit. Sometimes there'll be situations where it's in your best interest to simplify, especially if it's a situation where we're taking in a longer problem, because you might take a derivative, then use that derivative to do something else, and it just makes everything else more cumbersome. If you would have simplified it, it'll make all the following steps easier. Well, we'll deal with that when we get to longer problem, because we're going to get to the idea of taking a derivative and taking the derivative of the derivative and taking the derivative of the derivative. They call it a first derivative, second derivative, third derivative, and so forth. Especially in a situation like that, it really makes getting the second derivative will be a lot easier and less cumbersome if you simplify the first derivative. But like I say, do you have to? Absolutely have to? No, you don't absolutely have to, as long as your answer is correct. So there you go. Anyways, let's look at f prime. Let's look at f prime of x. So we got this whole mess here. Now we want to find f of 3 and f prime of 3. Why is that? Because we're looking at a graph at the point where x equals 30. We want to look at the tangent line and actually get the equation of the tangent line. So f of 3 is, we're going to plug in 3 into our function f, and that's going to ultimately give us, crunch out, we get negative 45. Now we're going to plug 3 into the f prime that we just figured out, and we plug 3 into here, blah, 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 we ultimately get 12. So now we're going to use good old point slope. So y minus y1 is equal to m times x minus x1. So my x1 is 3. That's given to us. The y1 is negative 45. That's what we just calculated. That's what we just crunched out. M is 12 because that's f prime of 3. So the slope of the tangent is going to be, at that point, is going to be 12. And that's going to give us y equals 12x minus 81. Now, why would you want to believe me when I say that's true? What do I know? I'm a big liar. So, but actually, before we get to that question, let's look at question B. The tangent line is horizontal at any value of x, such that f prime of x equals 0. In other words, if you want a horizontal tangent line, that means the horizontal lines have a slope of 0. So what we're basically going to do is we're going to take the derivative, set it equal to 0, and solve for x. So here's our derivative: 2x minus 9 times 2x plus x squared plus 6 times 2. And we're going to set that equal to 0 and solve for x, and we get either x is 1 or x is 2. So which one is it, 1 or 2? Well, it could be both. Could very well be both. And the tangent line is horizontal at x equals 1 and x equals 2. So let's check this out. So what I want to do is I want to go to Desmos and graph this. So f, as I said, let's go back to my original function. So here's the original function: 2x minus 9 times x squared plus 6. Let's go to Desmos and graph that sucker. Here we are, and very annoying. Just go to Desmos. And so what I say, y equals, it was 2x minus 9 times x 2. That's all. I'm just going to check that I got this right. X squared plus 6. I think that's what it was. Let me just check. 2x minus 9, x squared plus 6. And the other one is going to be y equals 12x minus 81. Y equals 12x minus 81. I'm going to make this, well, I can't even see it. So it's going to should be like a parabola. I don't know why I can't. Oh, that's right. It's not a parabola. It's a third degree equation. And now let's go to y equals 12x minus 81. It's going to be a little hard to graph. 12x minus 81. So we're going to go to y equals 12x minus 81. Oops. And let's put that in here. Y equals. Oh, you don't have to do this necessarily. I just want you to see that this is actually working here. And again, this is going to be a little tough to see just because, well, it's going to be very tough to see. So what I'm going to do is I'm going to make it a little bigger. Just focus in when x is 3 and y is negative. All right, so these guys are going to. So you want where I can't tell. Wow. Well, this is a little tough to. Let's see. What would the x is 3, 36. 36 minus 81. I'm trying to. It's a little. Let me see if I can make it a little bigger. I want to find, I want to kind of see. This is a tough thing to see on the graph. But here it looks like it's. Usually Desmos helps you with this. It gives you the. It's like a long time. Okay. Well, I see when it's 2.9, that's negative 40. See, yeah. But, by the way, if x is 3, 12 times 3 minus 81, that's 36 minus 81. That's negative 45. And you see we're kind of like in that. I'm trying to get it exactly on the right spot, and I'm having trouble with that. Usually Desmos helps you with that. Anyway, that's the best I'm gonna do. But you notice that, but as far as the other question is concerned, notice that when x equals 1, we have a horizontal tangent, and when x equals 2, we have that other horizontal. So B is easier to see. Can that be it right there? Ah, there we go, right there. So that's, yay, we finally got it. So this here is the intersection point, 3, negative 45, just like we said it would be. It's a little hard to see the picture, because it's so close and snuggy. And here's one horizontal. This will be one horizontal tangent. Of course, that will be y equals negative 49. That will be y equals negative 50. We get to 2. Why don't I put that in there? Y equals negative 49, and y equals negative 50. And notice there's our two horizontal tangents right there, and we're all this is all beautiful. and pow. So we have, that's one tangent, which again, it's a little hard to see. Let me just go down a little bit. And that's the other two tangents that are horizontal, and it's all good. So yay for technology. Okay. Let's move on. So I want to find it now. We had problems before. You may say, what's the point of, what do I even need this product? Well, if I have a product, I'll just multiply it out and get my answer. Well, that's not always possible, because you see, if it's 2x to the third times e to the x, I can't just say multiply it out and distribute it and do my, because I'm not going to get another polynomial. I'm going to get a whole, it's a whole different function, and similar here. So f prime is going to be 2x to the third times the derivative of e to the x plus e to the x times the derivative of 2x to the third. And that, if you crunch that all out, that's going to wind up being, and you're going to wind up, it's going to be 2x squared times e to the x times parentheses x plus 3. That's going to be the final answer. And for the ln, again, it's going to be 6x to the fourth times the derivative of ln plus ln x times the derivative of 6x to the fourth. Those are my two functions up here. And the derivative of ln is x is 1 over x. The derivative of 6x to the fourth is 24x to the third. So it's going to be 6 times, was ultimately x to the third, plus 24 times x to the third ln x. And I could factor out a 6x to the third. Again, you don't have, you could leave it, and technically, you could leave it like this guy right here, technically. Or you could simplify it a little bit like this, or you could just, or simplify it even more like this. Like I say, technically, even, if you would write this answer here on the test, this answer where I'm moving my cursor, technically that will be correct. Just saying. All right, let's move on. And okay, now it's time for the quotient rule. And the quotient rule, if you have a quotient that's a little bit bigger of a formula, it's this kind of similar formula, but a little bit bigger. So I like it, T and B, top and bottom. So the derivative of this overall quotient, y or f of x equals the quotient of these two other functions, T and B, is going to be b times T prime minus T times B prime over plane B squared. So that's the formula without all the x's in it. B times T prime minus T times B prime over B squared. There you go. And let's actually put this into action here. So we have some quotients here. Let's get these straight. Got some quotients. Let's just do these suckers. Okay, here we have a few examples. So now look at, I just want to make a point about C. Number C, I have x squared minus 3 on top and I have x squared on the bottom. I could, if I wanted to, I could just break this up into two fractions and just do the answer that way, not even bother with the quotient rule. In fact, we're going to do both of those things. But A, I'm not able to do that. X squared over 2x minus 1, you cannot just break that up into two fractions the same way, because when you can see, because whatever, numerator, denominator, I'll let you figure it out. Anyway, use the quotient rule with T of x equals x squared and B of x equals 2x minus 1. That's our thing here. So the derivative is, so it's going to be 2x minus 1 times the derivative of x squared minus x squared times the derivative of 2x minus 1 over 2x minus 1 squared. And you get 2x minus 1 times 2x minus x squared times 2 over 2x minus 1 squared. And you use simplifying it, and the final answer you get is 2x squared minus 2x over 2x minus 1 squared. And we're just going to leave the answer like that. And for the next one, we're going to do basically similar process, go through the whole, derivative, blah, blah, blah. And we finally get this guy down here, negative t to the fourth plus 2t cubed plus 2t minus 1. And that's just the, that is just the way it is. I just, let me see here for a second. No, okay, good. Moving on. And let's look at number C. Number C, I could use the quotient rule. So it's x squared times the derivative of 2x squared minus x squared minus 3 minus 2x minus 3 times the derivative of x squared over x squared squared. So we crunch, and we ultimately get to 6 over x to the third power, and it all works out beautifully. Now notice, had we split it into two fractions, x squared minus 3 over x squared, so we get x squared over x squared minus 3 over x squared, but 3 over x squared, I could rewrite that as 3x to the negative 2. Now, why do I want to rewrite it? Because in calculus, we learned the power rule, so I like putting things in terms of powers, in terms of exponents. Anyway, the derivative of this guy, well, the derivative of 1 is just goes on vacation, and the derivative of negative 3 x to negative 2 becomes negative 3 times negative 2 times x to negative 3, which is positive 6 over x to the third, which is the same answer we got here with the power rule, with the quotient rule. So I love the fact, I personally I don't know how to say it, how to explain this, but I love doing things different ways and seeing that you get the same answer. And it kind of shows the overall consistency of mathematics. That's just my personal thing. I actually just enjoy, people ask me like, why do I like doing this job? Why do I like, why do you get so excited about math? It's just a bunch of numbers. And I personally don't view it that way. To me, there's a certain beauty and certain art and certain artistic, I don't know what the word is, artistry and beauty in math. I view math as an art. That's how I always felt about it. That's just me personally. And I love seeing the consistency, the unity and the consistency within mathematics, and all the things that just work out and so nicely and beautifully. That's just me. I'm just sharing my personal feeling. This is not something you're going to be tested on. It's just how I feel. Different people feel differently about math. Different mathematicians feel differently about math. It's just the way it is. Anyway, if you talk to different mathematicians, they all like math, but sometimes for similar or same reasons, sometimes for different reasons. Everyone has their own thing, Anyway, so let's find f prime for f of x is equal to 2x. Oh, that's a match problem. Oops, wrong one. Example 5. Here we have 3 e to the x over 1 plus e to the x, and here we have ln x over 2x plus 5. So again, we're going to use the same quotient rule, but these are just different functions. They're not just polynomials. Let's just do it. So we have 1 plus e to the x times 3 e to the x derivative minus 3 e to the x times the derivative of 1 plus e to the x. And that's over 1 plus e to the x squared, because whatever's on the bottom, I just take it and square it. And crunch. Now I wind up getting 3 e to the x over 1 plus e to the x squared. And for the other guy, I do 2x plus 5 times the derivative of ln x, that's this b over here, minus ln x times the derivative of 2x plus 5. And I take the bottom 2x plus 5 and I square it, and crunch, and I get 2x plus 5 minus 2x times ln x. And like I say, technically, if you would leave the answer in a messy form like this, or if you leave it in a messy form like this, technically it would be correct. You would get full credit on a test. Again, the book is simplifying. I personally like it when you simplify it, but you're not required to. I just want to be clear about that. All right. By the way, my daughter got a 5 on her AP Calc. Not that I'm bragging or anything. But my daughter got a 5 on her AP Calculus test. So, not that I'm a father who likes to brag about his children or anything, but Anyway, here we go. Sales analysis. By the way, sales analysis is a huge thing, and it's a huge area of total sales and we're going by thousands of games of a video game T months after the game is introduced are given by this formula: S of T times 125 T squared over T squared as well. So we want to find the derivative, and then we want to find S of 10 and S prime of 10, and we want to use this to estimate total sales after 11 months. That's kind of an interesting question, and let's do one step at a time. So first, for A, we're just going to do the straightforward quotient rule. So it's the t squared plus 100 times the derivative of 125 t squared minus 125 t squared times the derivative of t squared plus 100. So again, I'm just taking the top of the box, top of the fraction, the bottom of the fraction. Crunch, and I finally get 25,000 t over t squared plus 100 squared. Now, what's S of 10 and S prime of 10? Well, fine. I just take the number 10, plug it into my original function here. That's going to be S of 10. Then I'm going to take the number 10 and plug it into this derivative guy over here. I mean, and if you do that, you get 62.5, and here you get 6.25. Isn't it interesting how they're different by a factor of 10? It's so interesting. And that means that total sales after 10 months are 62,500 games. And because 62.5, that means in terms of thousands, and the sales are increasing at a rate of 6,250 games per month. Now, since total sales will increase by approximately 6,250 during the next month, so the estimated total sales after 11 months is going to be 62.5, which is the 10-month mark, plus the estimated growth, which is what the derivative told us, 6,250, and that gives us 68.50. Now, of course, we could always just go to the original formula and just plug in 11 instead of 10, and let's see what happens if we do that. So 125. Let's see if I would just go to the original formula. 125. 125 times 11 squared. That gives me 15,000. Now I'm going to divide that by 11 squared plus 100. And so I'm dividing 15,000 by 221, and I'm going to get 68.43. And what did we get? And well, 68.438, that will be 68,438 games. And our estimate, our quick estimate, by just adding was 68,750. That's not bad. That's when you talk about thousands and thousands like that, being off by a couple hundred is not a big deal. I mean, it's not the worst thing in the world. I don't know. So because what is 750 minus? What is 750 minus 439? So 750. 750 minus 4. 700, but 700 out of 68, 68,000. That's not so horrible. Anyway, that doesn't seem right. 7,000, but something doesn't. I must have. Let's try that again. I must have hit the button wrong. 750 minus 439. Oh, 311, not 711, 311. So 300 out of 68,000. It's not it's not so horrible. If I would, what percentage is that? To say divided by 68,000. 6. It's kind of. That's like less than 0.5%. Okay. Anyway, so refer to examples. Oh, it's roll one. Oops. The next. It looks like so we're done. Okay, that's it. We're done. And that is the end of 3.3. That was a quotient lesson. I hope you enjoyed it as much as I did. And we'll see you guys next time. Bye.